Welcome back for another episode for our day all about machine learning. We've had several discussions. We saw a demo. We learned about Google and how it's using machine learning through the Intel One API. We had a roundtable discussion about machine learning at scale. And now we are discussing machine learning and the future of the data center. And let me introduce our first guest, Meena Arunachalam. How are you, Meena? How are you?
Hi, thank you. Thank you for having me. Hope you're doing well, Alex.
Yes, I am doing very well. Meena is a principal engineer at Intel. And our next guest is Paul Teich, Director of Product Management of Infrastructure at Equinix. Hi, Paul.
Hi, how are y'all doing?
Great, great. And so thank you both for joining us. And I am eager to discuss how we are starting to see the intersection of machine learning and the data center and how that's affecting end-to-end AI processes and how we are thinking about data center architectures that could provide those power and efficiencies to meet the demands of AI ML workloads. So I think maybe, Meena, one thing I'd like to know is, we hear a lot about Amazon and all the hyperscalers, Google and Microsoft, really investing heavily in machine learning. What can we learn from their data centers, and what can we learn about what's the next development beyond what we're even seeing from them?
Sure, that's a great question. So, in my role, I lead end-to-end AI optimizations, both at the software level and then hardware-software co-design, right? So, to be honest, the next AI workload or the what is going to come in the future has not even been created yet, right? So we all sort of uh, extrapolating and planning for um, what is to come in the future. We're building for the future, right? So some of the interesting things that we are seeing are looking at the problem holistically as a whole from the end to end, all the way from the data ingestion pipeline to the data pre-processing and feature engineering and whole host of other things, what quote unquote are called the AI tax that you pay to address any part of the AI application or the application's AI portion at heart, right? So we really need to speed it up because you really want to think about performance, efficiency, power consumed. So don't just focus on the AI algorithms or the really cool neural networks, which is important. But in order for you to get the best end-to-end customer experience or performance, you really need to look at the full picture. And that's what we do. I do in my role and trying to optimize all the pieces, whether it is parallelization, better vectorization of the code, or better overlap of data movement with compute. You have to be really smart applying AI, in the true sense of optimizing all the pieces of the puzzle, right? And
Right,
that's what I think we are seeing a lot of.
right. Paul, so what is that whole picture then? What is that picture that we're looking at and really using the hyperscalers as context for understanding what we are looking at?
So, part of what we do is provide platforms for folks to run AI on. So, our customers are doing all this neat training and inferencing, and my job is to give them the best platform possible to do that on. And you can kind of think of it like mass transportation. Um, it's great to own your own car. In some environments, that's not practical. If you're stuck on the highway at commute time with everybody else, it doesn't get you there any faster. And so there are mass transportation options. You can look at the biggest clouds like flying, taking a jet across the continent. Very efficient for a large number of passengers. We're kind of in the middle, and kind of like mass rapid transit, large buses running around. And what we do is try and make that more efficient. So what that means for AI is trying to understand customers' applications at the scale customers want to run them at. And so all AI kind of boils down to, for us, for our customers, is running some job. If you're training, you're trying to create a model to recognize patterns in data. So it all boils back to data, as Meena was saying. And if you're inferencing, you're actually throwing little packets of data at that trained model to try and figure out what pattern is recognized in that data you're being given. And both of those have different compute profiles and as importantly, power consumption and cooling profiles. So, the bigger your training task, you get into supercomputer cluster type activities. If you're doing something like smart speakers and trying to host millions of users on with an AI-driven smart speaker who can give you responses to what's the weather. I'm not going to use anybody's names on this, but you ask your smart speaker, they recognize that you're asking the smart speaker a question, and they have a certain amount of time to recognize speech, frame that in natural language, create a response. I'm in Austin. I am in Austin. What's the weather like here? And then go find that weather out of a database and say, oh, it's 98 degrees and about to rain. And reframe that as a natural language response and spit it back to me. And you have a fixed window of time to do that in which your users are going to get frustrated. And everything's like that, whether you're recognizing cat photos or doing whatever, you're actually, first thing that happens is data movement, but then you're doing something with the data in a fixed amount of time. If you're training a big model, your time frame may be hours, but you still, have to get a certain level of accuracy, and the model has to fit your commercial requirements or your research requirements. So we look at that as power spent and equipment costs.
Great. So Meena, when you're looking at that, many of these data centers run essentially on CPUs, right, on x86 architectures. But we are seeing the introduction of GPUs in data center environments. What is the dual role of GPUs and CPUs in these environments?
Absolutely. That's a great question. And I like to think of it as a continuum, right? So on one end, you have the general purpose CPU. Nowadays, we have things like DL boost or vector neural network instructions, which are fixed function units to do certain neural network ops, so to speak, really fast, for example, on one end of the spectrum. The other end of the spectrum, you can think of an ASIC, a very special purpose chip that is almost like you've coded your neural network in hardware, right? It'll be extremely fast, but all it can do is only that. And maybe in some cases, you are not going to change this algorithm or this network for the foreseeable 2-3 years time frame. So you're okay to do that investment, right? And then in between, you have GPUs, and then you have FPGAs, right? And then you sort of see this continuum. And depending on what, for example, inferencing really works out very well on the CPU, not just because it's general purpose, but it also is able to handle small batch sizes, right? If you have a batch size of 1, you just want to, batch size means basically, you're issuing an image and then you're saying, I want to know, classify this image, or I'm asking you a question. All I care about is what is around trip latency, right? I'm not worried about, are you able to do thousands of images per second, right? So those kinds of cases, CPUs will do very well. And then inferencing. So maybe if you want some extremely special purpose training, maybe you move down the continuum a little bit, right? To an accelerator, which is very special purpose. But the thing is, what you have to remember is, anytime you have to go off chip or to an accelerator, you're going to have to pay the cost of data transfer, data movement. And that you have to choreograph really smartly, and a lot of new techniques and technologies are coming up. And to hide these latencies, to not and be very efficient about these data transfers, and both in the hardware and software, you can play a lot of tricks. But at the end of the day, that is one of the constraints you have to think about. The other one is about your memory capacity, right? Accelerators are somewhat, I'm not saying they've made huge strides, but somewhat, limited in on their on-chip or on-device memory. Whereas in the case of a CPU, you can have, 6 terabytes or, in the order of many, many terabytes of both, either DRAM, or you can have Optane memory, persistent memory. And depending upon your use case, you will have to sort of pick and choose, right? And that's kind of, sizing. I would call it sizing, your perf per dollar, your TCO, your energy efficiency that you're looking for, and even your usage. Are you going to be wanting to run general purpose workloads and AI, which is a lot of times your bigger workload has non-AI components. Like I said in the beginning, it's an AI tax that you pay because you're building AI for serving a bigger purpose, for a bigger application, right?
So, Meena,
yeah.
Quick question. So also, when we're talking about processors versus GPUs, if you could speak a little bit about ensembles. So at this point in the evolution of AI and machine learning, we don't actually have like one model that we're using. Because if we had one model, we could actually like tune for it really easily. But if you could talk a little bit about ensembles, collections of models trying to solve a complete problem.
Sure, absolutely. In fact, I think the example you earlier had, like a chatbot kind of an example, right? So you have not only just ensemble of models, but ensemble of or many, many faces, right? So you have to get the speech signal, and then you do a speech synthesis and convert that into, speech to text. And then you probably have to, have a NLP model to understand what that question means and then come up with an answer. But then you probably go to a recommendation system, and then you recommend some songs or books or whatever for the question that was asked. And then you go on to the next phase, and then you convert your text back to speech, and then you complete the loop, right? This is just the, what happens there. But then you probably also have to comprehend things like talking back to your cloud, where potentially you might be doing some, learning or some running of your models. And then you have to decide when does it make sense to run things locally versus on the edge or on the endpoint device versus the cloud, and what is my SLA, my service level agreement with the user, and are all these latencies tolerated? I mean, so many aspects to think about. So in my mind, you have to, so it's a big optimization problem. And if you don't look at it as a complete end-to-end application, you sort of, there's a lot of inefficiencies, and on the same exact resource, you can harvest a lot more performance if you look at it as a full problem, in a complete, end-to-end problem, right, that you're trying to solve.
So in a way, I mean, focusing on the processor there helps reduce data movement, right? So we talk a lot about data gravity in the industry, right? And so, and for those who aren't familiar, data gravity is the concept that the more data you have, the more you want to keep it in one place, because you pay penalties for moving it from computer to computer, from server to server, from system to system. And so having it all in main memory with the processor actually helps reduce the latency between running pieces of the different models in the ensemble, and between assembling the pieces back for an adequate response. So I think that's part of what general purpose processors has to offer, where you can offload like critical parts that really need the computational power to an offload accelerator like a GPU or an FPGA, a special purpose ASIC. The thing there, though, is that now you're spreading the power as well, right? So anytime you're going to run something that does a task very well, and you're running it as fast as you can run it, with today's process technologies, you're actually generating heat. So these are typically 200 watt or greater heat sources. So you got a processor sitting over there at 200 watts. You've got a GPU sitting over there at 200 watts. You have main memory actually burns memory as well.
Yeah.
And so focusing on how to optimize that, I think the first level of machine learning is processor, general purpose, figuring out what you want to do until you can scale that.
And by the way, you are paying a cost and energy for data movement too. When
Exactly.
you're moving the bits through these wires, you're also paying. So yeah, you have to really plan out your data optimizations and choreograph this whole thing. Like it's almost like staging, data staging. At every time you do a handoff, you need to find out what is the most efficient way to do this, right?
So the network matters a lot, actually. So in terms of once you load data out of your disk space, out of your mass storage into main memory, maintaining coherent main memory across servers takes time, energy, latency is time. But having a really well thought out network architecture to support your processors and your data movement, I think is critical in AI applications in the future.
One of the questions I have is in terms of that efficiencies, is that one reason why we're seeing machine learning and serverless architectures have a coexistence that makes sense?
I would say serverless is, from our perspective, serverless is the convenience factor. So it's kind of the...
And you can turn it on and off, right?
Well, so it's different coding techniques. So serverless is a high level of abstraction where programmers can write a little bit of code to do a lot of things. The higher the level of abstraction, the less customization you can do. So if you're doing things that have been done before and those functions are available to do them, then serverless is a great way to just get off and running fast.
I like to call it function as a service.
Exactly.
There are definitely lots of servers.
It's got lots of servers.
So yeah, you're right. It becomes almost like canned functions that, if you are willing to give up a little bit of, customization and then you can definitely reap the benefits of fast, right? So I kind of like to think of the ML or the machine learning AI, is the fastest growing workload. It is the workload that hasn't even been created. Use cases haven't even been thought out yet. But I want to think of it as the data-driven part. Like how is an ML or an AI, model or an application different from a general application or a regular software engineering application? Is the data-driven portion, right? And on the same note, it gives you a lot of power to create things with the data. You're also very dependent on the data itself. By that, I mean the distribution of the data, the features. There's something called CACE. Change anything, you change everything. Even a hyperparameter in the model, a learning rate, or anything you touch in the model, or even the features, or even the data, new data comes in out of distribution data that you see can potentially change the model. So you really have to sort of create ML technologies. I'm not only talking about models, but the whole end-to-end pipeline of a model, with it in mind that it is pretty resilient and it can tell you if it is seeing things and it cannot figure out, because a lot of it is statistical based as opposed to a scientific base. Meaning, I can give you a funny example, like in an image recognition inference engine, if you do it naively and you've never trained it with giraffe images, let's say, and then you suddenly show it a giraffe image it's never seen because it's never seen a giraffe before, the softmax layer will go and overconfidently classify it with a 70% probability that it's a horse. Okay, so instead it should be telling, oh, I have not seen this. You have to have enough, enough uncertainty or things put into the model so that it can say, you know what, this is something I haven't seen. I don't know what this is, right? That's one example. Another technique is you can also do active learning or continuous learning. As you are seeing more and more new data, you sort of train the model to learn on its own too. But then neural networks are not human beings, right? So there is a concept called catastrophic forgetting, which is when it starts learning new things, it starts forgetting the old things. So you have to really architect your models very smartly, right? For that.
So, but it's all still about the data, right? When you're talking even about one-shot training, right? It's so. I mean, we still need the techniques that have been pioneered over the last 10 or 15 years in terms of big data hygiene. Just classic. Am I collecting an unbiased data set, a large data set? Is it representative? Is it clean data? Is this data that I can actually train a model on? And so archiving becomes important. Making sure that you can attest to where the data came from. Actually, there are lots of legal cases based on AI popping up these days, right? And so a lot of like non-deep learning things that have to happen around creating the data sets that you used and managing the data sets that you use to train this. So still, again, a great use of general purpose processors, also a big memory sink. So have you seen trends in terms of moving from like half a gig, 2 gigs per core? How do you look at memory resourcing and other system level resources when you're looking at either training or doing inferencing tasks?
Sure. One of the things, trends that I like that we have noticed in a lot of publications, that the model sizes themselves are growing quite a bit, right? And that doesn't mean it's a good thing, but billions of parameters and it's just continuing to grow. And it becomes a big challenge when you go to train a model. Now you have to do things like not just data parallelism, because the model itself may not fit into a single node. You have to chop up the model by layers and then do what is called model parallelism or hybrid parallelism. And then that brings about a lot of issues in terms of convergence and hyperparameter tuning. So I mean, I'm not saying that you should reduce the amount of memory, but as and when possible, techniques like pruning or looking for sparsity and, almost like densifying your model so that it's a nice, intact, efficient way to do the multiply, add, mac operations on them. You basically want to take a smaller footprint, especially if your devices, let's say you're on the edge, you have power constraints, you have thermal constraints, you have memory constraints, you have compute constraints, even you have network constraints because you cannot reach to the cloud and, back and forth. You may have to do a lot of, computing at the edge. So depending upon the use case, and in general, I feel I don't want to build a power plant for every model I want to train or, or deploy, because it's never one model, right? Like you said in the beginning, it's an ensemble of models, and data scientists are continuously building models. And the smartest data scientists are always prototyping, always experimenting. You want to give them a lot of these opportunities, but at the same time, also practice good discipline about creating, models that are sort of energy aware, compute, efficiently compute, efficiently vectorized, use caches wisely, use memory bandwidth properly, and then and make your end-to-end performance come together in a very, not just high accuracy, but high accuracy with high efficiency.
Great. I want to just see if any of our people watching would like to ask a question. We have a few minutes left and just want to make sure that there is that opportunity. I would love to think a little bit more about the future of the data center from that developer perspective. What is that? What they're the ones who are building out these models, and they're the ones who will be and their teams and their, operations teams of the future will be managing them. So what is the data center of the future for the developer? What is that world like? And developers will go where there's opportunity. They'll, if there's opportunity at the edge, they'll go there to, to start building upon it. But what is that? What does this mean for the developer?
Would you like to take it first? Okay.
Sure, go ahead.
I think developers are looking for flexibility and control. So we're still, as Meena said, we're not done with AI yet. We're still at the beginning of this. It's a long cycle in our industry, and so developers essentially want to control the machine that they're working with. They want all access to all the levers and knobs, and so I think bare metal is turning into one of those solutions that they're looking for. And again, processor based or with accelerator, but because within a deep learning software framework, you want access to all the performance that you can get because latencies are so important. You're trying to run a service of some kind, whether you're training a model to support the service or operating the model as the service. It just boils down to making money and doing interesting things. And that comes with time constraints and money constraints. So you want to fully utilize the gear that you are buying. If you're not doing that, it's expensive gear. So that's I think it's the old argument about serverless is great if you're dabbling, if you just want to experiment, get your feet wet, so to speak. But once you start actually getting into production environments, you absolutely want the best you can afford, and you also have to bear in mind the state of the art changes every 6 to 12 months in this industry. And so buying your gear locks you into an amortization cycle. So the old data center of your glass wall in your corporate data center where you're going to buy the latest enterprise deep learning gear, in 12 or 18 months, that's going to be horrifically out of date the way things are moving. And so having somebody manage your deep learning environment so that you can upgrade to the latest gear when you want to take that step and not have that weight of all of that equipment sitting in your own data center is another advantage of moving to clouds is we absorb that cost.
Yeah. Meena, why don't you take us out on that one? We're up at about a half hour. So I'd love to hear your point of view and we'll wrap it up.
Okay. Sure. Developers, I agree with a lot of your points. One of the things for developers is absolute productivity, right? Like you should be able to have high productivity in tools, ease of use, get to the level of modeling and coding that they really want to with really popular APIs, popular packages, and all to be very easy and ready to use, right? So the other thing that developers also want is really good hardware, good software and everything, but at the same time, things like auto hyperparameter tuning or auto ML, things that will sort of make their life easier, maintaining different versions of the models or even sort of serving these models in a production pipeline, easy to be able to use. So for example, there's a concept called, I used AI packs first, and there's another concept, a very popular paper from Google called the hidden technical debt. So there is a lot of data dependencies, there is model complexity growth, the versions of software is changing, new hardware is coming up, all these things are coming, and what is a developer to do when constantly they need to do continuous integration, continuous delivery, like you would in the true software engineering in the realm. In ML, there's another added one along with data, like what earlier Paul was saying, you have to worry about the cleanliness of this data. How are these systems integrated with each other? How are they coupled together, right? So many other aspects that they need to think. So I think it's not enough to just focus on, I want to optimize that piece of AI alone really fast, but think of the whole ecosystem, and almost like a data engineer is handing off to a data scientist who's handing it off to an ML engineer, right? Like the whole pipe goes. So I think even as developers or people, some of the skills that are going to be really very sought after are going to be those who understand the infrastructure and the AI. In the old days, we used to say hardware, software co-design. I'm going to say hardware, AI co-design, right? Where I'm going to understand my algorithms and my data and my modeling and all these techniques, but I also understand how to map enough. I know enough to map it to my infrastructure and how to keep it efficient and how to understand the flow and handoff that happens throughout and all the dependencies really well, so that ultimately I can make the the best end-to-end experience for the user and for the developer as well, right? To be the most efficient.
I want to thank you both for taking the time. That was a great way to end it, Meena. I want to thank you both again. Meena Arunachalam is principal engineer at Intel. Meena, thank you so much for your time.
Thank you for having me.
Yeah, that was a lot of fun. And Paul Teich, Director of Product Management of Infrastructure at Equinix. Thank you very much. And thank you both for really having a lively discussion. It was nice to just be able to sit back and listen. So thank you very much.
Thanks, Alex. Thanks, Meena. Good to talk to you.
Great job. Thanks. Bye, everyone.